same pattern we did with the weak acids and applying the concepts of equilibrium to weak acids. Now we're going to apply the concepts of equilibrium to weak bases. So here, once again, we have our generic reaction, but you can see it's written just a little bit differently, where we're just saying B for base. So like in the previous example, that could be the NH3, all right? But now with this generic base weak acid, generic weak base equilibria, we have to include water in the balanced reaction, because you can see that's what ends up creating the hydroxide, right? And so you can see what we create is a BH plus. So just so we understand how to use this generic style reaction, so for example, if B equals NH3, then BH plus has to equal NH4 plus. Okay, so hopefully that makes good sense, because we're going to see more than just ammonia for weak bases. So as long as we recognize we just add H plus to that formula, then we can apply this generic formula to any weak base. All right. And so now here we have KB. I told you we were going to play alphabet soup. So thus far we have KA, now KB, KC, and KP. So we're working our way through the alphabet pretty well already. Okay. So KB, as you might imagine, is called the base dissociation constant. Sometimes we could also just call it the base equilibrium constant, or even sometimes just KB. Okay. And so now if I'm writing this equilibrium expression, right, you can see that even though I have to use water in this weak base reaction to demonstrate how the hydroxide is produced, the H2O liquid does not appear in the equilibrium expression. Okay, so that's important. So now let's talk about this little table here. So in a weak base, KB is very small, and a strong base, KB is very large. And so really by KB being large for strong base, we mean infinite, because the reaction just goes to completion. There is no KB constant for a weak base. But KB is very small for a weak base, meaning the equilibrium position is far to the left. And so once again, that's what we see here. I don't have a strong base example, but I do have a weak base example. And you can see here the majority of the mass of this reaction is on the left once it achieves equilibrium. Okay. And so now what that means is for a weak base, our hydroxide ion concentration is much, much less than our initial base concentration. And again, we can see that on this graph here, right? The hydroxide concentration, as indicated by this blue bar, is much, much less than our B, our base concentration right here, okay? And so for the strong base, the hydroxide concentration will be basically equal to the initial base concentration because it dissociates completely. Okay, and I didn't put this on this thing right here, but for the weak base, we could say BH plus is a better acid than H2O. And so once again, if we were thinking about this generically, right, we know that when the base wants to react with H2O, in this case now the base is a proton acceptor, so that makes water the acid being the proton donor, okay? So now this is a similar situation where this reaction does not really go very far to the right. However, our BH plus reaction, reacting with OH minus, dominates as the reverse reaction because BH plus is a better acid than H2O. In other words, an acid being a proton donor, this BH plus wants to donate that proton to hydroxide much, much more. I'll draw that as like a thicker arrow, right? This proton donation dominates, which is why the reverse reaction dominates. And that's where we see the equilibrium position being on the left, okay?